Hi everyone, this is Mr. Henry, and in this video I'm going to be showing you guys how to perform a regression on a combined function. As we've learned so far, not all real-life scenarios can be represented by a simple function. For those that are not, we will model them using a combined function. This is a challenge because the software tools, like Excel, aren't really good at interpreting mixed functions. For this lesson, I have generated a set of data here in Excel, and you can see it here in Word, the actual equation, and we will be using some simple steps to find this equation again, and hopefully if this all works out, then our equation should look exactly like the one I used to generate the data. So here are the steps. We will perform a regression on the larger part of the combined function. We will get an equation of that, subtract it from the data, and then use our new data to find the other part of the combined function. So to show you what I mean, we'll work here in Excel. This is the data that I've generated using the function. Numbers are just 1 through 100. And I will take both of these and make a scatter plot. So as expected, our equation here was a sine function plus a linear function, and that is what that looks like. So we do see the oscillations here, and it looks linear. So now to get the actual equation of this, first thing I'm going to do, as the steps suggest, we're going to perform a regression on the larger part of the combined function. So in this case, the overall trend here is the linear function. So we'll perform a linear regression. And in Excel, that's as easy as right-clicking and hitting Add Trend Line. So I know that this is linear, so I'll leave linear checked here. And the key thing here is that you want to display the equation on the chart. Without the equation, we won't know what to subtract from our equation or from our data. So this is the equation of the line of best fit, and the line of best fit should hopefully be the same as the linear part of our function. And as we can see, they're pretty similar. So we had 0.5x plus 10. We got 0.49x plus 10.4. So it's not going to be exact, but pretty close. So the next step is to subtract this equation from our set of data. So over here in Excel, I'm going to use this equation and type it out so that we can subtract it. So equal sign, and then I'll type in the equation, 0.4908. And for x, I'm going to select the letter from our A column because those are our x values. I'm going to hit times first, and then plus 10.466. And there we go. I'm not going to do that 100 times. You just drag down from the little box in the bottom corner all the way down to 100. And then as you can see, this looks pretty linear. So what we'll do now is subtract that from the data. So that's as simple as equal sign our original data minus our line. And same thing, copy that down all the way to 100. Now to show you that it worked, what we're going to do is I'm going to graph both of those. So I want the original function plus the new one. Insert a scatter plot again. And there we have it. So we have the blue is the original function, and the red is the original function minus the linear part. Okay, to make our work a little bit easier here, I'm just going to take the graphs of our x and our new function in which we subtract the linear part and graph those in a scatter plot. I will put the little lines there to connect it so it looks a little nicer. Now, what you'll notice about most graphing softwares or algebra softwares like Excel, there isn't really a type of regression for sinusoidal functions. But not to worry, we've done questions like this before, where we had some sort of data and modeled it using a trig function. So what we're going to do is exactly that, model this trig function. So in order to model our trig function, we need our four variables, A, which is our amplitude, our K value, our D value, and our C value. So the amplitude is quite easy. We know the amplitude is the maximum distance from the center. So what I'm going to do is just take all of these and I'm going to find the maximum value. So say maximum, and I'll also say absolute value. So it'll take our negative numbers and count them as positive numbers. Okay. And we get 5.05. So that will be our amplitude of our trig function, which makes sense because originally when I made the data, we used 5. K, that is going to be 2 pi divided by the period. So in this case, we need to look at the period. So here we can see, you'll have to look over a few repetitions, but we can see that the data here looks like it repeats every 10 points. So after 10 points, we're back here. This is point 10. And then again at point 20, point 30, point 40. So 2 pi divided by 10 is the same as pi divided by 5. So, and that will be our value there, 6.628. Our D value here, you might have one later on when you're trying this, but in this case, you can see that it's not. This is our first point at 1, and it kind of starts at 0 if we had a point for 0. So our D value will be 0. The C value should be 0, and that's because of the work that we've just done. We subtracted a linear function so that we only have a trig function that is with 0 as the central axis. So that makes things pretty convenient at 0. But just to point out, when we do graph the whole thing and we get an equation that looks like this, this 10 could also be seen as the C value of our real function. Okay, so with that knowledge, we can now make a new set of data that models our real function. So I'm going to, up here, again, equals, because we're typing an equation, and then I will put in all of the data that we've come up with so far. So just to refresh my memory, I need to pull up our linear function. So our linear function here was 0.4908x plus 10.466. And when I am coming up with the new set, we'll need that because we're adding that on to our sine function. So equals, it was 5.05. I'll type some more digits there so we're a little more precise. Times sine our K value we calculated as well, so 0.628318, and that'll be times x, which remember is our A1, and then than the part of our linear equation, which was 0.4908, and again, times x plus 10. And I think I've typed that in the wrong box. Hopefully that's an easy fix. There we go. And then I will drag this down all the way to 100. And we have our data. So to verify that that all works, I'm going to graph our original data and our modeled data. So to highlight just these columns, in case you've been wondering, I'm holding down the Control key, and that allows me to select just these columns that I'm looking at, and then insert a scatter plot. And as you can see, zoom in a bit here, make the graph a bit bigger. The points that we have modeled using these steps is pretty close to our original function. You can see both the red and the blue. I believe the red is our modeled function and the blue is the original. So we have modeled this pretty exactly. Okay, so just to recap those steps that we took, perform a regression on the larger part of the combined function, which was the linear part. We got the equation of that, the line, subtracted it from the data to get just our sine function. And then we modeled that other part and then combined those two parts to one equation to get our combined equation. Now this would work if it was linear and sinusoidal, or quadratic and sinusoidal, exponential and sinusoidal, or any type of combined function. These steps would be very similar. So for homework, you guys have a set of data that we have sent to you. So for my class, I'll be giving it to you guys on the Google Classroom. And the Lychy's class, I don't know how he gives you stuff, D2L, I don't know, email. You guys can ask him. And for homework, you guys are going to follow these same steps and model model it using a combined function.